So last class we started these notes, but I thought I would make a video of them just to make sure everybody understands what's going on. So we're talking about horizontal tangents and graphs of the derivative. You have two goals. One is to find the local max and min of a function, and remember that the local max and min are just the points at the top of a hill or the bottom of a valley. So we're trying to find those points. Determine the graph of f prime of x given the graph of f of x. So first example says find the local max and min points of this function. So the local max is here and the local min is here. And if you remember, I had asked you guys the question, what is the derivative at those points? And because the tangent line is horizontal, we know the derivative is 0. So at this point's x value, the derivative is 0, and same thing happens down here. So the first step in figuring out what those coordinates of the max and mins are is to find the x value at which the derivative equals 0. So I have to find the derivative. So first thing is that I know my derivative is negative 3x squared minus 4x. And then I have to set it equal to 0. So I'm trying to find the x values where the derivative equals 0. So I can factor this, x times negative 3x minus 4. And now I know that each one of these factors could equal 0. So x equals 0, or negative 3x minus 4 equals 0. If I add the 4, negative 3x equals 4, divide, and we get negative 4/3. So now I know that the x value for this point is 0, and I know the x value for this point here is negative 4/3, but I still want to know the y value because it says that I need to find the actual point at which there's a max or a min. So how do you find a y value when you know an x value? So you plug the x value in. So the second thing is substitute x into the original. Remember, when you're trying to find a point, you're substituting into the original. When you're trying to find a derivative, you're substituting, or a slope, you're substituting into the derivative. So substitute x into original equation. So I'll do 0 first. So we get y equals negative 0 cubed minus 2 times 0 squared plus 4, and that gives you 4. So I know that the y coordinate here is 4. And the second one, y equals negative, let's see, what am I plugging in again? Negative 4/3. Okay, negative 4/3 cubed minus 2 times negative 4/3 squared plus 4. And I'm going to grab my calculator, and I'm just going to plug all of that in. And negative 4/3 cubed minus 2 times squared. And I'm getting 76 over 27. And that's approximately 2.81. Which makes sense because this y value looks like it's at about 2.81. So 76 over 27. So my final answers for where my max and mins are that one of them is at 0, 4, and the other is negative 4/3, 76 over 27. Okay? All right, next thing. A ball is thrown in the air with an initial upward velocity of 48 feet per second. The height of the ball after 2 seconds is given by this equation. So we have this equation that models the height of a ball. find the time at which the ball is at a maximum height. So if you imagine this graph, your x-axis would be time, and your y-axis would be height. So at a time of 0, you haven't thrown it at all, it's on the ground still. You throw it up, it's going to hit a maximum height, and then it's going to come back down. So I want to know at what time is it hitting that maximum height. So first thing I think, again, is that, okay, my maximum happens where the horizontal line, or where the tangent is a horizontal line, so the derivative is 0. So I'm going to take the derivative, so negative 32t plus 48, and I'm going to set it equal to 0, because I know that my derivative equals 0 there. And then we subtract 48, and I divide by negative 32, and 48 divided by 32 is 1.5. So that means that time equals 1.5 seconds. Now, that's the x value at this point, because x is time. So at 1.5 seconds, now my part B says find the maximum height. So the maximum height says, okay, if I know x is 1.5, I got to know the y value. So we're going to take that 1.5, and I'm not going to substitute it into the derivative because the derivative gives me the slope. I'm going to take the 1.5 and I'm going to substitute it back into the original equation to get the y value. So y equals negative 16 times 1.5 squared plus 48 times 1.5. And plug in my calculator, negative 16, 1.5 squared plus 48 times 1.5, and that gave me 36. What are my height units here? We've got feet, okay? Height is done in feet. So if I'm thinking about this graph, this maximum point is 36. 1.5 seconds, it reaches a max height of 36 feet. Okay? All right. Now, let's talk about graphs of derivatives. So you guys did an activity last class where you had a function, and I asked you to draw in the tangent lines, fill in a table, and then plot the graph of the derivative. So I believe that your graph last class looked something like this. And the derivative looked, I don't remember exactly. The derivative looked something like this. So if this is f of x, that this would be f prime of x. So we said f prime of x will always be 1 degree less than f of x. So for example, if f of x was x cubed, then f prime of x would have to be 3x squared. And these aren't the actual equations, I'm just giving you an example. So because you subtract 1 from the exponent, it always goes down 1 degree. This means that the graph will have 1 less curve. So if we started with 2 curves, then we go to 1 curve because the degree is decreasing by 1. Okay, the second thing about your graph, f of x has a horizontal tangent, then f prime of x will have, and that's an x-intercept. And that's because if this is if this graph right here is my f of x, right here I have a slope of 0. So let's say that occurs at negative 2. Well, if I'm graphing my derivative, that means at negative 2, it should be 0 because that tells me that the slope is 0 at that x value. The same thing happens here. Okay, so if the slope is 0 here, that must mean that the derivative equals 0 there. So those become x-intercepts. So this would be negative 1, negative 2. All right, 3. F of x has a positive slope, then f prime of x will be above the x-axis. And that's because, for example here, if the slope is positive here and the slope is positive here, well, that means that my derivative is positive. So if I go to the graph of the derivative, well, then the derivative must be positive or above the x-axis. If I think about the opposite, f of x has a negative slope, then f prime of x will be below the x-axis. So if I come back to my graph up here and I think about where is the derivative negative, so here I have a negative slope, so that means the derivative is negative. So that means my derivative should have negative y values. They should be below the x-axis. So positive slope, the derivative is above the x-axis. Negative slope, the derivative is below the x-axis. Where the slope is 0, the derivative should intersect the x-axis. So now let's see if we can match up some graphs to the original, to the derivative. All right, so let's start out first finding our x-intercepts of the derivative. So I know that that's going to happen where my original graph has a horizontal tangent, because that means the slope is 0. So here at 2, I know that the slope is 0. So if I come over here at 2, I know that must mean that it intersects the x-axis. Okay, next thing. Find out where the derivative is positive and negative. So plot above x-axis for positive slope. So I know that on this side here, my slope is positive. So that must mean that for all my x values to the left of 2, my derivative has to be positive. I'm going to make this a straight line, because I'm also thinking in my head that if my original's a quadratic and has one curve, my derivative must be linear and have no curves. And then last thing here, I'm going to plot below x-axis for negative slopes. So here I know my slopes are negative, and so that means that all my x values to the right of 2 on the derivative must be below the x-axis, and so it should look like that. And again, remember that if we started out with a quadratic, which is degree 2, my derivative must be linear, must be a straight line. Okay, let's look at one more example here. So same thing, I'm going to start out plotting where my horizontal lines are, or where my tangents are horizontal lines. So at -2 and +1, I know that there has to be an x-intercept on my derivative, because the slope is 0 here and the slope is 0 here. So at -2, the slope was 0, and at 1, the slope was 0. Now, here my slope is negative, and here my slope is negative. So to the left of 2, I have a negative slope, and to the right of 1, I have a negative slope. That must mean that my derivative is below the x-axis, because those would be negative values for the derivative. This is a degree 3, okay, curves plus 1, degree 3. So that must mean my g prime of x is degree 2. So this is going to look like a quadratic. So this is a cubic, degree 3, and this must be a quadratic, degree 2. I know that because curves plus 1 tells me degree 3, and I know this has to go down 1 degree. So I'm going to make this kind of curvy, like a parabola. Now in the middle, the last step here, I know that in the middle I have a positive slope. So that means my y values on my derivative must go above the x-axis. And so that's what your graph's going to look like. I think that's the last one. Yep.